Hi, and welcome to this talk on batch processing with AWS Step Functions. A little bit about me. So my name is Jamie Walker. I'm a solutions architect at Steamhouse in Manchester. Steamhouse are a cloud and DevOps consultancy. We're also an AWS Advanced Consulting and well-architected partner. And we cover the whole lifecycle of a customer's cloud journey, which includes strategy and architecture, build, migration, and we also provide a managed service. So a bit more about me. So I've been working with AWS for just over 2.5 years now. Prior to that, my background was as a Linux sysadmin. And these days, my main focus is on client delivery work. I currently hold 4 of the core AWS certifications, including DevOps Engineer and Solutions Architect Professional. Most recently, I've worked on containerized and serverless platforms. However, most of my general experience has been working with ECS and EC2 workloads. And finally, I'm a keen gamer and musician. So these are 2 things I enjoy doing in my free time between working and looking after my daughter. So the purpose of this talk, I'm going to deep dive into the AWS Step Functions service, what it is, how you can use it to coordinate multiple AWS serverless components using visual workflows. We'll cover some typical use cases for step functions, as well as some general best practices. And finally, we'll walk through a recent project that I've worked on where step functions solved a number of technical challenges. So before we discuss step functions, I'd briefly like to discuss the concept of state machines, what they are and why they're useful, because they're a fundamental part of the step function service. Okay, so they're used to break down large, complex tasks into independent, smaller tasks, which are linked by events. And progression between each of the states in the state machine is known as a transition. And if you look at the diagram below, these transitions are depicted by the connecting arrows that connect each of those states there. And each state can accept an input and produce an output. So from an AWS Step Functions perspective, their implementation of a state machine is a logical entity inside of the Step Function service, which controls the flow of the workflow. And it also manages the state of all the activities and the data flowing between each of them. So what is AWS Step Functions? So it's a service that lets you coordinate multiple AWS services into serverless workflows, so you can build and update your applications quickly. It allows you to orchestrate a workflow in a given order, and you can design and run your workflows that stitch together services such as Lambda, Fargate, and Amazon SageMaker into feature-rich applications. From our experience at Steamhouse, step functions have been particularly powerful for 2 high-level use cases. The first of which is to automate infrastructure tasks which rely on multiple AWS services. This could be a workflow to run ECS Fargate tasks to process data in a pipeline. Secondly, it can be directly integrated within your application using the SDK. So an example of this might be adding an email approval workflow to your application using a combination of services such as step functions, SNS, API gateway, and Lambda. And step function state machines can be executed manually via the console, on a schedule, or ideally automatically in response to an event, for example, an S3 event notification, and use Lambda. Okay, so what are the benefits of AWS step functions? So state machines can be visualized in the console, making it easier to view the various steps of your workflow. Workflows are robust, so your applications and tasks are executed in the order that you define. And step functions logs the state of each step, allowing you to diagnose and debug issues quickly. And it's serverless, so you don't need to worry about the management and the underlying infrastructure that runs the state machines. So how does AWS Step Functions work? So it's based on the concept of tasks and state machines. All the work in the state machine is carried out by a task. And a task performs work by using an activity or an AWS Lambda function, or by passing parameters to the API actions of other services. State input is in a JSON format, and states usually pass JSON as output to the next state. Now, there are 2 types of state machines available in AWS Step Functions. and these are standard and express workflows. Standard is aimed at long-running, durable workflows, and these can run for up to 1 year. They employ what's known as an at most once model, whereby your tasks and states are never executed more than once, unless you have configured retries in your state definition. We'll cover what that means shortly. But essentially, this means that they are more suited for things like processing payments, etc. The other option is express workflows, and these are ideal for high volume event processing workloads, for example, IoT data ingestion. And these workflows can run for up to 5 minutes, so quite a considerable difference to standard workflows. And they employ an at least once model, where there's a possibility that an execution may be run more than once. And both standard and express workflows can be triggered in response to events such as HTTP requests via Amazon API Gateway or event sources in Amazon EventBridge. Your state definitions are created using the Amazon States language, which is a JSON-based DSL. And we'll cover an example of that a bit later on. Now, Step Functions also offers a number of state types for different purposes, and we'll run through what each of those are now. The first of which is task, and we've kind of covered that briefly already. This is essentially where we want to carry out some work. The choice state is a decision tree, so we're making a choice between some branches of execution. That could be based on the input provided to the state. Fail or succeed states, so this is where we're able to stop a state with either a fail or a success. Pass, this is pretty self-explanatory, but it passes the state to the next state, and it will also pass in output its original input. Wait states, so this is where we're able to configure a delay for a specified amount of time. And finally, parallel and map states, both quite similar with some subtle differences, but in my opinion, this is what makes step functions really powerful. So parallel states allow you to run concurrent branches of an execution, for example, multiple Lambda functions with the same input. And map states, while similar, will execute the same steps for each element in an array that's been passed in as the input. Okay, so Step Functions supports a number of service integrations, all of which are listed on this slide. We've covered a couple of them already, but other examples include AWS Batch, Amazon SNS, SQS, EMR, and DynamoDB. And you interact with each of these services directly from your state machine via your state definition. And you do so using 3 integration patterns, and we'll cover what those are now. AWS provides 3 integration patterns for controlling your services in your state machine, and each has its own set of supported services as well as their own benefits and limitations. The first of which is request response. This is where Step Functions will wait for an HTTP response before progressing to the next state. All these services in the previous slide support this pattern. An example might be publishing a message to an SNS topic. Secondly, run a job. This is when using services such as AWS Batch or ECS and Step Functions, you can use this pattern to force Step Functions to wait for a job to complete before transitioning to the next state. For example, waiting for a long-running task within your application to complete before progressing to the next state. And finally, wait for a callback with a task token. So here, the workflow is paused until a task token is returned. This is useful for processes that require things like manual approval or when you need to integrate with third-party services, etc. For example, this might be a workflow that passes a message including the task token to an SQS queue, which triggers a Lambda function. And during this time, the Step Functions workflow is paused while the task token is returned. So you also have to consider that express workflows are much less flexible in terms of the services that they support, and as well as their integration patterns. Okay, so move on to some use cases now. So these are just common use cases provided by the AWS docs. The first of which is transcoding media files. So using this particular example, you can see is based on a user uploading an image to an S3 bucket. And this S3 bucket has an event notification configured to invoke a Lambda function, which starts a state execution. And there are a number of states inside this state machine that use Lambda to thumbnail images, transcode videos, process logs, and index files, etc. Moving on. So the next use case would be to publish events from serverless workflows. So we can integrate SNS to trigger notifications regarding the success or failure of a workflow. And SNS allows you to filter the message and trigger another service, for example, API Gateway, or to simply notify a team member of a failure, including the error type and the state where the workflow failed. Now, of course, we could always pipe these messages out to like Slack, etc. Finally, we can coordinate container tasks in microservices and serverless applications. And as you notice from the previous two examples, they all follow the same kind of design pattern, whereby a file is uploaded to S3, a Lambda function is invoked, and the Lambda function is the thing that actually starts our state execution. In this example, the Lambda function is triggered by the S3 event notification, and it makes a decision based on what the optimal compute resource is for this task, based on some conditions, and in this case, it's the file size. And there's a choice state inside the step function, which triggers the relevant task either on Lambda or Fargate based on the state input. Okay, so now we'll walk through a number of best practices to consider when designing our step function workflows. So firstly, we're encouraged to implement retries. So retries are a powerful feature of AWS Step Functions, and they help to reduce the amount of time spent implementing complex retry logic into your applications. When a state reports an error, the default course of action for the interpreter is to fail the whole state machine. Errors are identified by case-sensitive strings, known as simply as error names, and the Amazon States language defines a set of built-in strings naming the well-known errors. Now, runtime errors can occur in any estate. So these can be caused by things like task failures, i.e. an exception thrown by a Lambda function. And your state definition can include a field named retry, which contains an array of objects known as retriers. And a retrier represents a specified number of retries, so how many times we want to retry this state. And each of these retriers must also specify an error name to act on. So this might be one of the error names provided by the states language, or this could be a custom error from your application. So we're encouraged to use timeouts. So stuck executions can occur when step functions receives no response from a task. Timeouts are configured by default, and again, like retriers, they're defined in your state definition. They're especially useful when trying to identify any issues, for example, when tasks aren't responding in an acceptable time frame. Moving on, so we're also encouraged to use fallback states. So these are similar to retries in that we can control how the state machine handles different types of errors. When a state reports an error, and either there is no retrier configured or the retries have failed to resolve the error, then the interpreter scans through the catches in array order. And when the error name appears in a state's catcher field, the machine transitions to the state defined as next in the workflow. And this provides us with some control and flexibility about how errors are handled. Okay, so state payloads. So if the data passed between states exceeds 32 kilobytes, you should be considering using S3 to store it, or the state you could risk your state machine being terminated. Workflow types. So types can't be changed after the state machine has been created. So I encourage you to read the docs and understand which workflow best suits the requirements of your use case. And finally, we're encouraged to avoid the history quota. So this is the record of events in your state machine. There's a hard quota of 25,000 entries in the history. So if you think you might be getting close to or exceeding that limit, then you're encouraged to implement a pattern which starts a new execution to continue the workflow or the job. Okay, so I've recently been working with a company called SPERRY Rail, who are migrating onto a new platform which leverages AWS Step Functions. SPERRY provide rail services globally, rail health services globally, and testing for testing rails for cracks and other issues. So the SPERRY engineers have been working. I've been working with over there. I've developed an AI system called ELMA, and ELMA is used to inspect thousands of miles of ultrasound scans collected by their inspection vehicles, searching for evidence of cracks in the rails. Now, SPERRY engaged with Steamhouse via the well-architected partner program to leverage our experience of building secure, high-performing, resilient, and efficient architectures. Now, the objectives of this engagement were to refine ELMA and to adopt more serverless services, as well as implementing a managed build CI/CD pipeline leveraging AWS services. And finally, the architecture. So Steamhouse worked with SPERRY to refine the operational system and the original design to take advantage of AWS Step Functions and ECS Fargate. Okay, so just a little bit more about what ELMA does. And it's described quite well in this infographic, but we'll focus on the process of how the data is captured and its progression through the workflow. So it starts here. So the data is captured by SPERRY's vehicles and is stored in their proprietary T1K file format before being uploaded to their on-premises database servers. The files are then pushed to an S3 bucket, which invokes a Lambda function and subsequently their step functions workflow. And the data is then processed over a series of steps before being packaged into XML files and delivered to their data scientists. So when reviewing the architecture, we considered a number of requirements, which included reducing the time it takes to consume these files and to start processing them, as well as making the platform more repeatable using infrastructure as code. So let's take a look at the original design following the shift from EC2 to ECS Fargate. Okay, so as you can see in the infrastructure diagram here, there are a number of moving parts, including multiple Lambda functions, SQS queues, and ECS services, most of which are tied together using logic inside of the application code. The main problems with this design are that the application relied on workers polling SQS queues to consume and process individual jobs, which caused two problems. The first of which is slow and complicated to scale because while it's simple to scale ECS tasks or EC2 instances in an auto-scaling group based on the number of messages in a queue, in this particular design it's impossible to scale down these tasks. This is because some of the ECS tasks, for example, the AI processing tasks here, now known as ELMA Predict, can run for several hours at a time. So there's no guarantee that when you scale in, you won't be terminating a task that hasn't finished its job yet. This also means it's not very cost effective because there are usually surplus tasks running in the service, since we can't scale down easily. Also, when there are no messages in the queue to consume, the ECS service scheduler will still launch tasks to maintain the desired count defined in the service config. And interestingly, you can see at the beginning here on the left side that step functions was already in use. However, it's just for a small proportion of the application workflow. So let's take a look at the refined design. Okay, so the main difference you'll notice here is that step functions now controls the entire workflow end to end. So state execution is still triggered via the same approach, i.e. a file is uploaded to S3, which invokes a Lambda function, and in turn it starts a state execution. And state and the data which was previously stored in SQS is now managed by the input and output of the various steps in the state machine. We also have the same choice state as we enter the state machine, which transitions to either the new XML or new T1K lambda states, depending on the state input, i.e. the file extension for that particular uploaded file. The new T1K lambda then carries out some processing before transitioning to the T1K Fargate task state. And this ECS task previously created 3 messages and pushed these to an SQS queue, each containing various bits of information which describes a job and the configuration needed for that job. The second ECS service would then launch tasks which would consume these messages one at a time and carry out the jobs. Now in the refined design, so what you see here, this task simply transitions to the get run IDs lambda function state here. Which is, so the lambda function is used to retrieve all the job IDs for this specific T1K file. And these IDs are then stored in an array in the states output and passed to the next state as input here. So here we use a map state to run concurrent Fargate tasks in parallel. And the map state iterates over the array input and runs an execution for each element. The array element is also passed into the execution of each map state as input. So each task here is a map state execution. And eventually results from these tasks are produced and pushed to S3 before being delivered to SPERRY's data scientists. Okay, so how does this look in the state definition? So this snippet you can see describes our map state. And the items path field at the top there, this is used in a map state to select an array in the input. And if the input to the map state is a JSON array, it will run an iteration for each item in the array, passing that item to the iteration as input. And in this example, we're using the $.runIDs node from our JSON input provided by the getRunID state, as previously explained. And the state machine will iterate over each element in this array, running an ECS task for each of them. So we pass in the array element, the run ID, as an environment variable into the container definitions field as well, which exposes the run ID for this job to the container so that it can gather all the information it needs for that run, as opposed to passing the entire set of configuration via an SQS message. So the benefits to this new design, so it's entirely serverless now. When there are no files to be processed, for example, so no S3 files being uploaded, the compute infrastructure is idle. This means the cost is minimal, and the main costs at this point are just data storage. So when a new file is pushed to S3, the workflow begins immediately, and we're no longer waiting for capacity to become available anymore. And also that means that we can spawn infinite jobs concurrently, and we just need to ensure that we're not hitting any service limits, for example, the maximum number of concurrent Fargate tasks. Okay, so the execution history. So Step Functions console provides the execution history for each state machine. And it provides a visual chart describing the flow for that execution. And it also presents a table showing each event in the state machine, including all the transitions in the workflow. And in this example, we're also able to view the type, so the type of transition, and we're also able to view the logs and the actual Lambda function code directly via the provided links, which if you have any errors in your state can make debugging issues a bit easier. Okay, so how did we manage the deployment for this infrastructure? So at Steamhouse, we use Terraform to manage the orchestration of most of our customers' AWS infrastructure. It's a great tool, and we're all big fans of it. And in this case, it's used to orchestrate the deployment of SPERRY's AWS infrastructure. And in the snippet you can see there, we have the state machine resource, just at the bottom here. And we have a template file data source at the top there. And these both comprise our step function state machine. Now, a template file data source in Terraform, this allows us for data to be fetched or computed elsewhere, to be used elsewhere in your Terraform configuration. So an example might be using the AWS AMI data source to fetch the ID of a registered AMI with some specific tags. This could then be used to launch in your launch configuration resource for an EC2 autoscaling group. So in this example, we use the template file data source, which renders a template from an external file, which is our state definition JSON file. The template file data source supports the vars argument, which allows us to pass variables into our template. So there's no need to hard code resource ARNs anymore, which means it's cleaner and encourages more cleaner and repeatable code. And finally, the state machine resource, we pass our template file data source as an input to the definition argument using the rendered attribute, which is the final rendered template of our file. Okay, just moving on to cost briefly. So just a quick note on the cost associated with the AWS Step Function service. So like many services, it runs on a pay-per-use model. So pricing does differ for standard and express workflows, and we'll discuss that in a moment. And AWS Step Functions falls under the free tier, so you can have 4,000 state transitions per month on standard workflows, and this also falls under the always free category of free tier, which is good. So standard and express workflows. So standard workflows are charged per transition at 2.5 cents per 1,000 state transitions. And express workflows are charged based on the number of requests for the workflow and the duration at $1 per 1 million requests. Now, referring back to the SPERRY case study, just to kind of give you an idea of how step functions might help with cost optimization, I've reviewed the costs associated with SPERRY's EC2 workload on their operational platform versus the step functions and ECS Fargate on the new platform. And I found that we've been able to make a saving of around 57% on their compute resources month over month in April. And a large part of that is because operational infrastructure was always on, and scaling up or down is fairly slow. However, now each Fargate task is launched on demand for the amount of time required, which obviously will likely result in cost savings. Okay, so just to summarize, so AWS Step Functions is a managed service. The orchestration is handled by the service as opposed to application code, which leads to simplified workflows. And that's it. So if you have any questions, please feel free to drop me an email or add me on Twitter or LinkedIn. My handles are at the bottom there. And I hope you enjoy the rest of the event and look after yourselves. Thank you.